Okay, here's the warm-up for today. So you have several questions here. The first question deals with the property of equality, where you're going to have to make the bases the same and then set the exponents equal to each other. The second one is where you actually would get the exponent and its base by itself and then use logs to solve it. And then number 3 is just setting up an exponential equation using one of our formulas there on the board, which I think I pointed to. So we're going to look at the first question. So to understand how to do this, you have to understand how 4 and 16 are related. And so hopefully, we start to get pretty quick at this and be able to recognize that 16 is just 4 squared. So if we assume that 16 is 4 squared, we can actually replace 16 with 4 squared. And so what ends up happening is this ends up being 4 squared, and then that 2 multiplies to the exponents that are already there. So what it ends up being is 4 to the 6x, forgot the parentheses, 6x plus 4, and then equal to this side, just 4 to the 2x. Now that the bases are the same, you can set the using the property of equality, you can set the exponents equal to each other to solve for x. By subtracting 6x, subtracting 6x, I get negative 4x equals 4, therefore x equals negative 1. And that is using the property of equality to solve for an exponential equation. The second problem is a little bit different. The second problem, I need to actually get the exponent and its base by itself. So everything else needs to go to the other side. So we start by adding the 14 over to the other side, giving me 1/5 times 3 to the x equals 4. Now, to get rid of the fraction 1/5, there's a couple ways you can do that. You could divide both sides by 1/5, or simply multiply both sides by what's in the denominator. The 5 times the 1/5 will cancel that out, leaving you with 3 to the x equals 20. Once the exponent and its base is isolated, you can now proceed to using logs. So we're going to log both sides of the equation. By logging both sides of the equation, it allows us to take this exponent and pull it down so that it's now x times log of 3 equals log of 20. The final step will be now to just get x by itself, so we would divide over the log of 3 to the other side. That'll cancel, and so I get x equals whatever the log of 20 divided by the log of 3, which is 2.727. And so that's solving logs, or that's solving exponentials using logs. Okay. Go. Exponential solving by property of equality, making sure the bases are the same, setting the exponents equal to each other. The getting the exponent and its base by itself. So adding the 14, multiplying by 5, and then once you get the exponent by itself, you log both sides to pull the exponent down and solve for x. The last problem, this was born out of, if any of you guys know Mr. Bruick. Mr. Bruick next year is going to be teaching in Dubai, and we got to this conversation, and he told me, he's like, "Did you know that Dubai was actually is actually only about like 50 years old? They built the entire city from scratch. It's all the rivers and everything, water, grass, everything that you see there is completely man-made because it's in the middle of a desert." And I thought that's just crazy. And so I looked it up, and it has actually grown. It's been doubling its population every 10 years. It's just insane. So it turns out that it was created from scratch, built from scratch around 1960. Since then, it has been one of the fastest growing cities in the world at 8% growth per year, which is just astronomical. 8% growth per year is crazy. So, but this is a perfect example of exponential growth. If they started with, and that's a typo. Just realized that this is a typo. It's supposed to be 30,000 right there, not 300,000. Hopefully on the board it says 30,000 and not 300,000. I don't remember. But it started with 30,000 people in 1960. How many people are living there today? Assuming 8% growth per year. Well, I pointed to the equations. Remember, there's two equations you will use. One is y equals ab to the t, and that's your traditional exponential growth. And there was the y equals ae to the kt, and that's for continuous exponential growth. And that's for more so like decay and stuff. Remember, e is only used for continuous, and then nowhere in this problem does it say continuous. So we're going to use the y equals ab to the t power. So all we're going to do is fill everything in. So a will represent the initial value, which is 30,000. B represents the growth factor. Now we got to be careful here because that's different than percent growth. Percent growth is actually the value R. So in order to find B, we have to use the second equation there that's on the board. And I'll just sort of slide over a little bit and change colors. The equation B equals 1 plus or minus R. Now, because this is growth, we're going to be using the plus. So it'll be B equals 1 plus 8%. Another place here we got to be careful is 8% is not actually the number 8. 8% as a decimal is 0.08. And so when we add those, you get 1 plus 0.08, which is 1.08. And that becomes my value of B. So in parentheses here, I have 1.08 then to the t power. And that's the equation that you're going to use. Now, because it says, it started in 1960, and how many people would live there today, we have to just figure out, well, how many years have passed since 1960? If you do the math, this is 2018, from 1960, that's going to be 58 years. So, since 58 years is a time, it's going to go in for t. So 300,000, sorry, I keep doing 300,000. 30,000 has 1.08 to the 58th power. And that would just be simply done in your graphing calculator. You can just put the whole thing in there, and you end up with y equals, and actually I have to put this in there. Excuse me. 30,000. 1.08 to the 58th power is 2,604,348. Now I know there are decimals there, but remember we're dealing with numbers of people, so you can't have decimals of people. So I'm just going to round. So that's 2,604,348 people, which is pretty accurate. I think the current population right now is about 2.5 million people, so it's pretty accurate. So the second part of this is a little bit more complicated, because this requires us to find when. If the growth were to continue, how many people would live in Dubai in 2050? So now we're going out further, and we're using our model to project populations in the future. If the growth were to continue, how many would live in Dubai in 2050? So now we have to figure out how many years are from 1960 to 2050 and use the same equation. So y equals 30,000 times 1.08. And how many years are between 1960 and 2050? 90. Plug that in your graphing calculator, and you get 30,567,453, I think, if you round. Which, if the growth were continue, that would make Dubai one of the most populous cities in the world. I think Mexico City is around like 35 million people, which is just insane. For a city that was only built in 1960, if that growth continues, that would be astronomical. That would be a very, very, very large city at 30 million people, but that's how you solve it. Please talk to each other, talk to the people within your group if you guys have any questions before taking the quiz. We'll obviously go over these quizzes next time I see you on Monday. Good luck.